So this is section 8.5, problem number 8. These are partial fractions. The whole idea behind partial fractions is that we need to take a fraction which we don't know how to integrate and make it into two separate fractions that we do know how to integrate. This is an example of where you have separate linear terms, and so typically what you do first is you try to see if you can factor the denominator. And so we can in this case. Let's just look at it by itself before we do anything. So this can be broken up into 2x minus 3 and 2x plus 3. So let's write it as such. So that doesn't help us out any at this particular point. But the method of partial fraction says that we can now create two separate fractions that have these as denominators individually. And that process is something that's separate from the integration part. So we can do it separately, and then once we get the result, then we can just put the integral signs in front of it. So we're going to look at 1 over 2x minus 3 and 2x plus 3. So these are, if we factor these, x would equal 3 halves and x would equal negative 3 halves would be the roots of the equation. But what we do is we create two fractions. And when you have independent, I remember what the name is here, I've already forgotten, discrete, I think it is, yeah, discrete linear factors. Is that what it's called? Distinct linear factors, that's what it's called. Okay, so they're distinct because they're different. And so one is plus 3, one is minus 3. Okay, now, so basically what we end up doing is combine these two terms with a common denominator, which is the same as this, and then we find out what values of a and b will make that work. And typically we just deal with the resulting numerator. So the long way would be to multiply this term by 2x plus 3 and 2x plus 3 in both the numerator and the denominator, and we multiply this by 2x minus 3 in the numerator and the denominator, which would be each case multiplying by 1. And then we'd end up with the same common denominator. And, well, let's just do it. Let's do it that way, a little bit of the long way, at least for this first problem. So you'd have, this would be a divided by 2x minus 3, and then we'd multiply by the other denominator in both the numerator and the denominator. So this is the other denominator, and you do the same thing for this term. So the term originally is b divided by 2x plus 3, so we multiply by 2x minus 3 and 2x minus 3. And what that does for us is we now have the same denominator in all those terms, so we can just look at the numerator. And so what we would have is 1 is equal to a times 2x plus 3 plus b times 2x minus 3. And when you have just two distinct linear factors like this, all you have to do is cross multiply. You'd say a times this plus b times that. You can see you get the same result. Okay, so now what do we do? How do we choose A and B? And there are only two choices. Well, when you have distinct linear factors, it's easy to do this. You could multiply it all out, and you could then group the terms that involve x and the terms that involve the constants. So you have two equations and two unknowns, and you could solve that, but that's making it longer than it needs to be. So you look at the roots of these particular equations. What value of x do these go to 0 at? And again, hopefully in the future you'll be able to figure that out, but let's just look at them separately. So 2x plus 3 is equal to 0. When does that happen? When x is equal to negative 3 halves. And you'd get that by subtracting 3 from both sides and then dividing by 2. So that will make, if we let x equals negative 3 halves, this will go to 0. Likewise, we take the other equation that's in the parentheses. So we set that equal to 0. Okay, what values of x will that go to 0 for? Well, we add 3 to both sides and then divide by 2, and so you'd end up with positive 3/2. So what we're going to do is we're going to choose those values of x separately, and what that will do is we'll cause each one of these to go to 0 in sequence, and that will get rid of one of the constants, and then all we'll have is one equation to solve with one unknown. So we're going to do that over on this next page. So the first thing we're going to do is we're going to say, let this equal x equal that, and plug it into that equation. So if we do, so let's say let x equal negative 3/2. Then what happens? We get 1, which is left-hand side, a times 2 times negative 3/2 plus 3. So that's the first term, and then we do the same thing to the second term. So we have plus b times 2 times negative 3/2 minus 3. Well, this is going to be 2 cancel out, so you'll have just negative 3. Plus 3 is 0, so this goes to 0. And so what we end up with is 1 is equal to b times, okay, the 2's cancel out again. And we're just multiplying 2 by this term, not by both terms. So these cancel out, so you get negative 3 times negative 3, which will be negative 6. And therefore b is equal to negative 1/6. Okay, so we do the same thing for the other part. We let x equal 3/2, which is our second choice here. And like a similar thing happens, you'll have 1 is equal to a times 2 times positive 3/2 plus 3 plus b times 2 times positive 3/2 minus 3. Okay, so this one's going to go to 0. 2's cancel out. 3 minus 3 is 0, so this goes to 0. And in this case, we get positive 6 in the parentheses. Therefore, a is equal to positive 1/6. So those are the numbers, a and b. And so the final answer, I'm just going to insert that down here. So we'll just extend this, and then we'll use a different color. So the final answer for the partial fraction part is we have a, which is 1/6. So we have 1 over 6 times 2x minus 3 plus b, which is negative 1/6. Let's put a negative sign here. So we get negative 1/6 2x plus 3. So that's what our original fraction was equal to. If we go all the way back up to the top, this was equal to that, and that is equal to this. So now what do we do? Okay, now we integrate it. So I'm going to add a page in between here. So rather than integrating this original fraction, which we don't know how to do, we integrate these two fractions. So now we're integrating 1/6 times 2x minus 3 minus 1 over 6 times 2x plus 3, the whole thing times dx. Well, these are going to fit into natural logarithms, and that's how a lot of these work. When you have distinct linear factors, they're always going to be natural logs. So to do that, let's u equal 2x plus 3. Therefore, du is equal to 2x dx. And you can see that if we let v equal 2x, actually I should have used minus 3 here, since that's the first equation. So that's minus 3. This is plus 3. You can see that the differentials are the same, 2x dx. Nope, got it wrong here. It's just 2 dx. Okay, sorry. 2 dx, and this one is 2 dx. Okay, so we have dx. We just need 2. So we would multiply these by 2 and divide by 2. Or we could put the 2 right here. That's probably the easiest thing to do. So let's, I'm going to rearrange this a little bit before we do the integral. I'm going to factor out the 6th. I'm also going to factor out a negative 2, a half. That's because I'm going to multiply by 2 to get 2 dx. So we'll end up with 1 over 2x minus 3 minus 1 over 2x plus 3. And that whole thing will be multiplied by 2 dx. Let's get this 2, because that cancels out that 2. Then the 6 comes out. Now we can do the u substitution. So we'll have 1/12 the integral. First integral will be 1 over, this is u, and this is du. And then we'll have negative 1/12 times the integral of dv, and this is v. So both of those are natural log, the natural log of u. So we'll have 1/12 the natural log of u, absolute value of u, minus 1/12 the natural log of the absolute value of v, plus our arbitrary constant c. And now we plug back in u and v, which were up top here, right there. So let's expose those. So we'll have 1/12 the natural log of the absolute value of 2x minus 3 minus 1/12 the natural log of the absolute value of 2x plus 3 plus c. And that could be just about right. We can do two more steps. We can use the properties of logarithms where, because we have a negative sign here, we can factor out the 12. So we have 1/12. And this would end up being the natural log of the absolute value of 2x minus 3 divided by 2x plus 3, all added to our arbitrary constant c. And I think I just realized, well, no, they did ask us to solve the whole thing. Just looking at the answer, and everything looks good. So we're done. Okay, we're on problem number 9, section 8.5. Again, the first step in trying to use partial fractions is to see if we can factor the denominator. So let's just write the denominator down. So we're going to have x, of course, in the first terms. And we're going to have negative 2 and 1, positive 1, or positive 2 and negative 1. So because we need a positive number here, we're going to have more positive than negative. So we'll put positive 2 there, and therefore we'll put negative 1 there, and that'll result in the right answer. So now what we're going to do is we're going to try to rewrite this as a fraction, two fractions involving these factors. So what we do is we start with the original equation. But we can go ahead and do the factored form. So this is just this equation with the numerator, denominator factored. And then partial fraction says if we have distinct linear factors, we have some constant a divided by one of the linear factors plus the constant b divided by the other linear factor, like that. And now we have to figure out what a and b are to make things work out. Because there are only two factors, we can just do a cross multiplication to get what we need, and then we keep the left-hand side the same. So we just have 3 is equal to a times this. We have a times x plus 2 plus b times x minus 1. So the next thing we do is we look and decide which values of x allow each of these terms respectively to go to 0. So you can look at them hopefully now and just say, okay, I'm going to let x equal negative 2. That will make that go to 0. So one of our choices of x will be negative 2. And if I choose x equals 1, that will also go to 0. So we apply one each one of those separately to find A and B separately. We can not have to worry about solving simultaneous equations. So if we let x equals -2, then we get 3 is equal to A times 0. -2 plus 2 is 0. And the second term is B is -2 minus 1. So that says we have 3 is equal to -3B, therefore B is equal to -1. Okay, so then we let the next thing happen, which is let x equals 1. So we get 1 is equal to A times 1 plus 2. X is 1, 2 is still 2. And the second term goes to 0 because that's why we chose x to be 1 as one of our two choices. So here we find out that 1 is equal to, oh, let's see, I've made a mistake here. This should be 3. Okay, so 3 is equal to 3A. Therefore, A is equal to 1. So now we've got A and B. We can go back and then plug those back in to here and then integrate them. So let's go ahead and let me write A and B down here. Now I'm going to use a different color that we're coming back. So B is equal to -1 and A is equal to 1. And therefore our original integral is, let's add a page. So our original integral now becomes the integral of A, which is 1, divided by x minus 1 dx. And then B is negative, so we'll have negative the integral of 1 over x plus 2 times dx. So these are easy. Anytime you have, there's no coefficient in front of x, and you have a constant added, it's just the natural log of the absolute value of whatever's in the denominator. Likewise, we have the same thing happening here, negative because of this negative sign. And then we have the natural log of x plus 2 plus our arbitrary constant c. Again, you can use the properties of logarithms to combine those two. So it's this divided by that. So we get the natural log of the absolute value of x minus 1 over x plus 2 plus our arbitrary constant c. And that is the correct answer. Test. This is problem 14, section 8.5, partial fractions. So first we look at this, it's different than what we've seen before in that the numerator has x cubed. Up to this point we've had like 1 or 2 or 3, some constant over that. So the question is, what do we do? Well, anytime the order of the numerator is higher than the order of the denominator, we have to use long division to create a new form, which will include a linear term, which will be easier to integrate, and then a fraction that we can solve using linear partial fractions. So we're going to use long division because this is just too crazy to do otherwise. You can't use synthetic division because you need to use synthetic division. You need something like x plus 1 or x minus 1. But we're dividing by x squared plus x minus 2, so that's not going to work. So we're going to do this the long way. So we're dividing x cubed plus 0x squared plus, actually minus x plus 3. And you got to make sure you include a place for the ones that are missing. And then we have the denominator, so what we're dividing by. So what we need to say is, okay, what can we multiply x cubed by to get x squared by to get x cubed? Well, the answer is x. You always look at the highest order term and see what you need. So if we multiply that out, we got x times x squared is x cubed. We have x times x, which is x squared. And we have -2 times x, which is -2x. And so we're going to subtract that. So when we subtract that, that goes to 0. That was the whole point in choosing x. And then we'll have negative x squared. Then we have a negative times a negative is a positive. So we have plus 2x minus x gives us plus x. And then we have plus 3. Okay, so the next thing we do is we go to the next place and we say, okay, what number do we need to multiply x squared by to get negative x squared? Well, the answer is negative 1. And then we multiply it out. So negative 1 times x squared is negative x squared. Negative 1 times x is negative x. Negative 1 times negative 2, positive 2. Okay, then we subtract that. So again, these are going to drop out. Negative x squared plus x squared is 0. So we have positive x, and then we have a negative times negative is a positive, so we get 2x. And then we have 3 minus 2, which is 1. So after this, what does this all mean? Well, it means that we can rewrite this original quotient as this term, x minus 1, and then the remainder, which is going to be plus 2x plus 1 divided by the original denominator. So this we know how to integrate easily. It's going to be x squared over 2. That'll be negative x. Here we have to use partial fractions to rewrite it. So that's what we're going to do. So we're just going to look at this part separately. So what we're looking at doing is we're looking at 2x plus 1 divided by x squared plus x minus 2. And we can factor the denominator. It's the same, I guess it's the same as the previous problem. Is that right? That looks awful familiar. Yeah, it's the denominator in problem number 9. So anyway, the way we factored this is going to be x plus 2 and x minus 1. So we set that up as the left-hand side of the equation. And the right-hand side will include the 2 independent linear factors, distinct linear factors. And so again, we have a divided by x plus 2 plus b divided by x minus 1. Now, even though we have an x up here, it doesn't change anything. Everything's fine. We don't have to put an x anywhere. Anytime you have distinct linear factors, you just have a or b, just have constants. We'll see where you end up including some variables in the numerator on the right-hand side. So again, we cross-multiply those two terms, and then you'll have the same common denominator. So we have a times x minus 1 plus b times x plus 2. And then we do the same thing again. We're going to let x equal 1, so that'll go to 0 first, and then we're going to let x equal negative 2. That'll let that go to 0. So let's add another page. So let x equal 1. So we get 2 times 1. Okay, so I have to put 1 in for there. And then we have a times 0 plus b times 1 plus 2. And so this is 4, and that's 3, sorry. 2 plus 1 is 3. 3b. So b in this case is positive 1. The last time it was negative 1. X equals negative 2. So we take 2 times x, which is negative 2, plus 1. That's the left-hand side of the equation. The right-hand side is going to be a times negative 2. And then we have negative 2 minus 1 plus b times 0. So we'll have negative 4 plus 1 is negative 3. And a is multiplied by negative 3. So if we solve for a, we'll end up with 1 again. So both a and b are 1 for this particular case. So our final integral that we're going to do is the linear part, which was x. Let's go back to the beginning here. Is x minus 1. So we have x minus 1. And then we have plus the two fractions. We have a over, what was that? X plus 1, x minus 1. Actually, x. A over x plus 2. So it's 1 over x plus 2 plus 1 over x minus 1. All four terms multiplied by dx. So we integrate these. We'll get x squared over 2 minus x plus the natural log of the absolute value of x plus 2 plus the natural log of the absolute value of x minus 1 plus our arbitrary constant c. And again, we can use the properties of logarithms to combine those two. And so what will happen is we'll have x squared over 2 minus x plus the natural log of x plus 2 times x minus 1 plus c. And we can just multiply that out. And really we need to include these, still keep the absolute value signs in there. So we'll have the absolute value of x squared plus x minus 2, the whole thing plus c. So just checking the answer. And we're good to go. So that's the answer. Problem 18, section 8.5. Okay, to this point we've dealt with functions that have distinct linear factors. This is the first example in the homework where we have repeating linear factors. That means that we have the same number here in the factor. We have it squared. So that's what it means by repeating. And what we do is when you have a repeating factor like this, you just write your expression slightly differently. So just like before, we would have some constant a divided by x minus 1. And then we have a constant b. But because we've already done this, we do it again. And so it'll be x minus 1, but we'll square it. So those are two different fractions that can have the same common denominator. Well, we already have this multiplied. This already has the same denominator as that. And you say, well, why do we even need to do it? Well, because we can get rid of this x term, and it just becomes, it'll become something that we can integrate. And I'm just thinking about something. No. I mean, I think there's a way that you could do this problem that we've done before where you would see if this derivative of this equaled that, and you could rearrange it. So there's probably more than one way to do this problem, but this is the way we're doing it right now. So we don't have to adjust this numerator at all because it already has the common denominator. This one we need to multiply the numerator and the denominator by x minus 1 to get the same denominator. So when we multiply this out, the first term a will be multiplied by x minus 1, whereas the second term will not be multiplied out at all. Okay, so now what do we do? Well, b is always going to be included in here, so we could, there's two ways of doing it. One is you can do what we've done before, and you could let x equal 1, and that would allow you to solve for b. And then once you know b, you could then just solve for a. So that's probably the best way to do it. So in this case, we don't have two choices. We just have one choice. This is going to go to 0 when x equals 1. So x equal 1. So you have 2 times 1. We let x equal 1, so we have to do that on both sides. And then we'll have a times 1 minus 1, which is 0, plus b. And therefore b is whatever is over here, which is negative 1. And so we can then plug b in as -1 and solve for a. So is that true? Yeah, I mean, we can pick any arbitrary number. So let's let the second one be x equals 0, and then we can figure out what a would be. Okay, so the second choice is completely arbitrary. It's usually 0 is the easiest thing to do. So what will happen is the left-hand side will become 2 times 0 minus 3 is equal to a times 0 minus 1 plus b, which we now know to be -1. So here on the left-hand side, we'll have -3 is equal to -a, because we have -1 times a is -a, minus 1. So we'll add 1 to both sides. That'll give us -2 is -a. Therefore, a is 2. So we have b is equal to -1, a is equal to 2. So now we can plug those in to here and have the integral. So this integral can be rewritten as a over x minus 1. A was equal to 2. So we have 2 over x minus 1. And then we have that's times dx. Then we have plus the integral of b. b is -1, so we have -1 divided by x minus 1 squared dx. Okay, so this one's going to be the natural log just like it was before. This one, we're going to use the u substitution, and u is just going to be the term in the parentheses. So u is x minus 1, du is equal to dx. And so we have dx already up here. So the first one, we'll just go ahead and integrate it. It'll be 2 times the natural log of the absolute value of x minus 1. The second part, we'll have the negative sign, which I'm going to just put out front. So this -1 just comes out front as a negative sign. And then the integral of that will be, well, what do we have before we do it? Let's not get too far ahead of ourselves. So dx is du, so we have du over u squared. And the integral of du over u squared is just u to the -1 divided by -1. We add our arbitrary constant at that point. So we have 2 times the natural log of the absolute value of x minus 1. The negative signs cancel out, so we have plus u to the -1 is the same as 1 over u, but u is x minus 1. So let's review what we did here. The negative signs cancel out, so it becomes positive. U to the -1 is the same as 1 over u, and u is x minus 1. So anyway, that's problem number 18. And I'm looking at the answer in the book, which is correct. There is one additional thing we could do, which is the fact that you could take this square inside. Now, they don't do this in the book, but I'm surprised they don't. But what you would have is natural log of x minus 1, the whole thing squared, plus 1 over x minus 1 plus c. And since you square that, I'm trying to decide here, can we do that? Because what happens is, yeah, I think you do. Yeah, I think it doesn't make any difference. So we can do that. So I don't see why we can't do that. So we just have the natural log of x minus 1 squared. We can take the absolute value sign off of there. Since we're squaring it, it'll become positive as a consequence. Okay, so that's the answer. Okay, well, we're going to start number 21, and we're going to finish 21. So this is going to be an example of where we have a combination of a linear factor and a quadratic factor, because we can't factor that completely. And so what we do is we factor it initially. So we can factor out an x is the first thing that we can do. So we have x times x squared plus 1, and we cannot factor x squared plus 1 to get a real number, because if we set this equal to 0, you'd end up with a negative 1. X squared is equal to negative 1. Square root of negative 1 is I, but that's not a real solution. So now what we're going to do is we're going to take this fraction, we're going to break it up into two separate fractions. And when you have linear and quadratic terms like this, the linear term in the denominator is just going to have a in the numerator. So if I had x plus 2, I'd put a over x plus 2. In this case, it's just x. The quadratic term, you put bx plus c. And that's always when you have a quadratic term. So if you have a linear term, you just have a constant. If you have a quadratic term, you have a constant times x plus a constant. Now, like we did with distinct linear factors, if you only have 2, you can cross-multiply these 2 to get the final result, and that'll give you the same common denominator. So we would take x squared minus 1 is equal to a times x squared plus 1 plus x, which is this denominator, times bx plus c. Okay, so this is obviously going to be something that's different. And you can't use that trick where you set x equal to one of 2 values so that you can eliminate it. As you can see, you can't eliminate anything. And I already see, no, I guess I did that right. Okay, yeah, I'm doing okay. So the way this works is you multiply everything out, and then you group the terms that have similar variable parts to them. So you're going to have an x squared part, you might have an x part, you might have a constant part. And then we are going to match up those parts so that you're going to have a coefficient on the left-hand side in this case of 1 times x squared plus 0 times x minus 1. On the right-hand side, we'll also have corresponding equations. We'll end up with 3 equations and 3 unknowns, and then we have to solve for the 3 unknowns, a, b, and c, from that. So, and usually they're not super hard. You don't have to use, typically one's easy to solve, and then you can substitute that into the other 2 equations to get 2 equations and 2 unknowns, which we know how to solve through elimination or substitution. So let's just open another page. Put these on the same page. So we're going to leave the left-hand side the same until we get everything grouped. So the right-hand side will become a x squared plus a plus b x squared plus cx. So that's distributing a to these 2 terms and x to those 2 terms. Now we're going to group them according to their variable. So we have x squared and we have x squared. So we get x squared times a plus b. So over here we had the a distributed. Now we're going to pull out the other parts, which are the variables. We only have 1 term that involves x, and we only have 1 term that involves a constant. So the 3 equations are associated with the x squared. So what do we have as far as multiplied by x squared? Well, on the left-hand side, we just have 1. On the right-hand side, we have a plus b. The second equation is the x's. Well, there are no x's on the left-hand side, and there's c x's on the right-hand side. And then, as far as the constants are concerned, we have negative 1 on the left-hand side, and we have a on the right-hand side. So we have 3 equations and 3 unknowns, but one of them is trivial. C is equal to 0. The next one we have is a is equal to negative 1. And so if we solve for b in the first equation, you'll get b is 1 minus a. So b is 1 minus a minus 1, which is 2. So we have b is equal to 2, a is equal to negative 1. And therefore, this original fraction can be rewritten as negative 1 over x plus 2x over x squared plus 1. So let's write that down here. So what we can say is x squared minus 1 divided by x times x squared plus 1 is equal to negative 1 over x plus 2x divided by x squared plus 1. There's no c because c was equal to 0. So now this is what we integrate, is this thing. So we're going to, instead of integrating this expression, which we don't know what to do about, we end up integrating negative 1 over x plus 2x over x squared plus 1, this whole thing times dx. Well, the second part we're going to use u substitution, so let's just do that. U is equal to the denominator, which is x squared plus 1. Therefore, du is equal to 2x dx. So 2x dx is du. So let's break this into two integrals. The first one won't require u substitution. We have a negative sign, 1 over x dx. The second one, we have the integral of 2x dx, which is du, divided by x squared plus 1, which is u. So when we integrate it, this will become negative the natural log of the absolute value of x. This one will become the natural log of the absolute value of u. And we add our arbitrary constant c. Then we substitute u back in, so we'll have minus the natural log of the absolute value of x plus the natural log of the absolute value of x squared plus 1 plus c is equal to 0. And again, we can use the properties of logarithms. This minus that can be combined into x squared plus 1, which is a positive term, divided by x, which is the negative term, plus our arbitrary constant c. So that is the answer associated with that.
Recording started.
Okay, so we're going to do problem number, what number are we doing? Problem number 24, section 5. And as you notice, I've got me on the screen. Not that I'm going to do it every time, but just so that you know I do exist. There is a real me at the end of this voice. So anyway, let's look at problem number 24. So we're doing the integral of x squared. Let me put my book up here so I can see a little better. Okay, so I've got x squared minus x plus 9 divided by x squared plus 9 quantity squared. Okay, just hold on a second here. I'm going to close my email down so I don't have to listen to that. Okay, the whole thing times dx. So what we have is we have a fraction that involves the denominator is a repeating quadratic. And so just like with repeating linear factors, we have the term by itself, and then we have the term squared. So what we're going to do is we're going to just look at the rational function first, and then we're going to decompose it into two fractions. And once we do that, then we can do the integration. So because it's a quadratic term, we have ax plus b divided by the quadratic term by itself. And then we have cx plus d divided by the quadratic term squared. Now this can get fairly long and complicated, so we have to be very careful about not making sure we make any mistakes. So make sure you try to concentrate as much as possible. Okay, what we have is this term already has the same common denominator that we're looking for. But this one needs to be multiplied by x squared plus 9 again to get x squared plus 9 quantity squared. So what we'll end up with is the the left-hand side numerator, and then we'll have ax plus b times x squared plus 9. So that'll give us the correct common denominator, and then we add the final two terms. Now, what we do is we're going to multiply everything out, and we're going to group the terms according to, in this case, x cubed, x squared, x, and the constant. Before we do that, we have to multiply everything out. So we use FOIL on this particular product, and so we'll have ax cubed. So that's that. And then inner will be b times x squared. Outer will be 9ax, so this times that, and then last will be b times 9, so 9b. So this is that multiplied out, we get 4 terms. And then we have the 2 terms remaining over from the repeated linear factor, repeated quadratic factor. Okay, so what do we have? Well, let's group them first, and then we'll write down our equations and see where we go from there. So we only have one x cubed term. As far as x squared is concerned, we actually only have one of those as well. So we have bx squared, then we have 2 terms that involve x. So we'll have 9a plus c times x. And then our constant terms are going to be 9b plus d. So we'll have, in terms of the x cubed terms, we have 0 on the left-hand side. On the right-hand side, we have a. So we just match those up. As far as the x squared terms are concerned, we have 1 on the left-hand side, 1 times x squared. On the right-hand side, we have b. As far as the x terms are concerned, we have -1 on the left-hand side, and we have 9a plus c on the right-hand side. And then the constant terms, we have 9 on the left-hand side and 9b plus d on the right-hand side. So we've got 4 equations and 4 unknowns, but 2 of them are explicitly already figured out. A is 0, B is 1. So if A is 0, here we know 9 times 0 is 0, so we have C is equal to -1. So let's write these down. So A is equal to 0, B is equal to 1, C is equal to -1. And the final one, we actually have to do something. We'd have 9 is equal to 9 times b, which is 1, plus d. And so we have 9 and 9 here, so d is going to be equal to 0. So given that, let's add a page and make this 2. So what we can do is now we can rewrite this with our known values of a, b, c, and d. So our original fraction now will become 2 fractions, and we will have a, which is 0, plus b, which is 1. So we get 1 over x squared plus 9. And then the second term is c, which is equal to -1. So we get -1 times x plus d, which is 0, all over x squared plus 9, quantity squared. So this is what we're actually going to integrate. We're going to have the integral of 1 over x squared plus 9 times dx. And I'm just going to take the negative sign out there. Negative x over x squared plus 9 quantity squared dx. So our original integral involved this, but we can rewrite it as this. And both of these integrals we can actually solve. So let's look at this one first. I'll use blue for that part. So we would say u is equal to x, so u squared is x squared. A is equal to 3, so that 3 squared is 9. And this involves the inverse tangent. So if we go to page 520, we have the result. And so the integral of, so when we rewrite this integral in terms of u and a, and also du is equal to dx, derivative of u is du, derivative of x is dx. So this will become du over u squared plus a squared. And that integral from page 520 is 1 over a times the arc tangent of u over a plus c. So given these values of u and a, the first integral will be 1/3 times the arc tangent of x, which is u, over 3, which is a, plus c. Okay, so that's that part. Let's add another page, and we'll do the second part, and then we'll combine them together. So what is the integral of x over the quantity x squared plus 9 squared dx? Well, in this case, let's use red. U, in this case, is going to be x squared plus 9. So du is equal to 2x dx. So we go back to the original equation, and we divide by 1/2, or divide by 2 in front of the integral. We multiply by 2 inside the integral, which we can do with constants. Can't do with variables, but we can do with constants. So you can see now I have exactly du, and here I have u squared. So we get 1/2 the integral of du over u squared. And we can write that as 1/2 the integral of u to the minus 2 du. When you integrate that, we'll get the 1/2, which is a constant. You get u to the minus 1 power divided by -1, plus our arbitrary constant c. So ultimately we get -1/2, and then 1 over u. U to the minus 1 is u to 1 over u. And u, so let's just do that. And then finally we plug u back in. And so u is equal to x squared plus 9. So that's the second part of this integral. So we can combine those two together. And so the total integral that we're looking for, and if we go back to the original page, which I don't know whether we can see here, the original problem was x squared minus x minus 9. So that integral, and actually I can look it up in the book here so that I don't have to go back. Anyway, problem 24 said, what is the integral of x squared minus x plus 9 divided by the quantity x squared plus 9 squared dx? Well, it's going to be equal to that integral. So we get 1/3 the arc tangent of x over 3 plus the second integral, which we have a negative sign there. So it's going to be -1/2 1 over x squared plus 9. And we can combine the two arbitrary constants together. So that should be the answer, but we'll just check here and stop for just a second.
Recording started.
Okay, so I see I've made a mistake here. There's the negative sign here with that negative sign, so this becomes positive. Otherwise, we're in good shape as far as solving the problem is concerned. Yep, that's it. Okay, just got to keep track of those minus signs. And so what it asks is to use the method of partial fractions to verify the formulas. And so the formula says that we have 1 over a squared minus x squared dx is equal to 1 over 2a natural log of the absolute value of a plus x over a minus x plus C. Okay, so that's the formula, and we want to use the method partial fraction. So what we're going to do is we're going to look at this fraction, and we're going to rewrite it as two fractions. Now, you can factor this. So before we do that, we have to factor the denominator. So we have a plus x and a minus x. You can see that's where those come from up here. Okay, so that's the thing we're trying to get to. And so because these are independent, these are discrete linear factors, we just have to do that. And so when you have discrete linear factors, you just take two factors and do as such with them. And notice I could factor out a -1, but I'm not going to do that. That would change the sign of everything. But I'm just going to leave them with x as being plus and minus. Before we would have had x plus a and x minus a, but it's equally valid to do that. So to get this expression with the same denominator as the combined fraction, we need to multiply this term by a minus x and a minus x in both the numerator and the denominator. Likewise here, we multiply by a plus x and a plus x in the numerator and the denominator, which would be giving us 1, of course, and doesn't change anything. And rather than writing that out, whenever you have two linear factors like this, you just have to cross-multiply them. So what we'd end up with is 1 on the numerator on the left-hand side, and you'd have a times the denominator of the second term, which would be a minus x, plus b times a plus x. So you take this times that and that times that and add them together. Okay, so even though previously we would have set it equal to the number here, equal to whatever it was, a, to get this to go to 0 and do this to go to 0. So we do the same thing, but we use a instead of a number. A is a constant, so it is still a number, but it's not a variable. This is a constant. So let's say let x let x equal a. What does that do for us? Well, we'll get 1 on the left-hand side. We have a times a minus a plus b times a plus a. Okay, so that goes to 0, no matter what a value is. So we'll have 1 is equal to 2a times b, and therefore b is equal to 1 over 2a. Okay, we do the same thing, letting x equal negative a. So let's, rather than, I'm just going to scoot this over, and we'll do the second one here in a different column. So if x equals negative a, what do we get? We get 1 is equal to our constant. We're trying to figure out our unknown a, and we have a minus a minus a. So we have a minus a minus a. And then the second term would be b times a plus a minus a. Okay, so I'm using the negative a here. Well, you can see these cancel out. And here you would end up with 2a as well. So we'd have 1 is equal to 2 small a, capital A. Therefore, a is equal to, I'm just thinking, did I make a mistake here? A minus, didn't seem to. It just seems like the answer, the final answer is going to involve something other than, seems like there ought to be a negative sign there. So let me just think if there's anything I've done incorrectly. So, I don't see it right away. See, what I'm thinking is, here I've got these things divided out, so there has to be a negative sign. Oh, that happens when we integrate it. Okay. I was trying to figure out where the negative sign came from that would result in us having a quotient instead of a product, but it actually happens when we integrate it. So let's add a second page. And so ultimately what we're integrating, instead of this fraction, we integrate two fractions, and they're the same. We have a over this. A is 1 over 2 small a times, so this is a, that a, and then you multiply by a plus x times dx, so that's the first term. And then we'll have plus the integral of b, which is also 1 over 2 small a. And you have 1 over a minus x dx. So those are the two fractions that we end up with. And a is a constant. So a can be brought outside the integral. We're integrating with respect to x, not with respect to a. So we could actually bring out 1 over 2a out of both integrals. Now, in each one of these, we do u substitution. The first one, we let it be the blue u, is a plus x. Therefore, du is equal to dx. And if we use the green u, that's a minus x. So du is equal to minus dx. And therefore, we would rewrite this as negative dx, but we'd have to put a negative sign right there. So those two negative signs will cancel each other out. And when we integrate these, it's just the natural log of whatever's in the denominator. So the first term will become 1 over 2a times the natural log of the absolute value of a plus x. And we get a negative sign here, so we get negative 1 over 2a times the natural log of the absolute value of a minus x plus arbitrary constant c. And if we factor out a 1 over 2a, then we would end up with the natural log of the absolute value of a plus x minus the natural log of the absolute value of a minus x plus c. And anytime you have natural logs that are subtracted from each other, you can rewrite that as quotient. So you'd have 1 over 2a times the natural log of the absolute value. I'm trying to decide, okay, so we take the absolute value of everything. So we would get a plus x in the numerator, and then we have a minus x in the denominator. And so that is our answer. So that's how that one works. I already know it works because I've already done the problem.
Recording started.
Okay, this is problem 55, section 5. And it gives us 3 examples. It wants us to evaluate or state which method we would use. We don't necessarily have to do the integration. We just have to state the method. And so we look at this and we'd say, okay, we can use partial fractions on this because we can factor x squared plus 2x minus 8 is going to be equal to x. So you'd have plus 4 and x minus 2. I knew these had to be either 8 and 1 or 4 and 2, and then when I saw this was positive 2, I knew the positive term had to be greater than the negative term. So I said, okay, maybe it's going to be 4. So if this is 4, that's negative 2, and you end up with a positive 2x. So you could use partial fractions for this, but it turns out that it would be easier just to do a direct u substitution. So if we let the denominator equal x squared plus 2x minus 8, then du is going to be equal to 2x plus 2 times dx. And we could look at the original equation. We could see we had x plus 1 here. This is the same as 2 times the quantity x plus 1 dx. So we just multiply by 2 here and divide by 2 there, and then we'd have du matched exactly. And so that would save us, but it would only work with x plus 1. If it was x plus 2, then it would not be so easy. We would have to use partial fractions at that point. And that's what happens in the second problem. So in this case, because the derivative of the denominator does not equal the numerator, or just the numerator times some factor, then we would use partial fractions. So we'd have 7x plus 4, and we'd factor just like we did in the previous example. And then we would have two distinct linear factors. So we'd have two terms, a over one linear factor plus b over the other linear factor. And we'd find a and b, and they would be constants. And then we'd have the integral. And so, one term would be the natural log of x plus 4, and the other term would be the natural log of x minus 2, all multiplied by these specific or corresponding factors. So that would be the second part. And then the third part, if we think about it again, we talked about in class that if b squared minus 4ac is greater than 0, then we have a real root. So let's just plug that in there. We have 2 squared minus 4 times a, which is 1, times c, which is 5. And so you'd end up with negative 16. And therefore, because it's less than 0, you can't factor this. And as a consequence, you could, you say, well, maybe I should use partial fractions. Well, you really don't need to go any further than this, because there's only one quadratic term. And if there's only one quadratic term, then you would just use the arctangent. So what we would do is we would take the denominator and we would use completing the square to rewrite that. So we don't need to put a 0 there. It's already 0. So what we would do is we would take half the factor in terms of in front of x, which is 1, and we'd square it, so we'd add 1. And we have our 5 remaining, and then we'd subtract 1 to balance this 1 that we added. So this would become x plus 1 quantity squared plus 4. So this original integral would be 4 over x plus 1 squared plus 4, which is 2 squared. So then we'd use a substitution that u is x plus 1, du is equal to dx, a is equal to 2, and then we'd be able to use the arctangent as the solution, because it fits. Once we made those substitutions, we would have, and I forgot the dx up here, you'd have 4 times du over u squared plus a squared, and this integral is on page 520 as a simple integral. So that's how you would do that problem.
Recording started.
Okay, so we're going to do problem number 59, and let me go. Okay, so I'm recording. I'm still trying to figure out this video thing. How you get it to be big. I think it's supposed to be like that when you're make video follow moderator focus. No, it doesn't do that. Okay, just playing around here. Oh well, doesn't really matter. Okay, let me go to the actual lesson here. Stop fiddling around with the video. I'll figure it out another time. So problem number 59 is a word problem, and it says the predicted cost in hundreds of thousands of dollars for a company to remove P% of a chemical from its wastewater is shown in the table. And what they do is they take that data and they make it into they do a curve fit of it, and they find out that this model fits the curve better than most of them do. So what we want to do is find the average value for this between 75 and 80%. So to find the average of something, you take 1 over the range of x values, which is 80 minus 75. You integrate from a to b, 75 to 85, of the value of the function multiplied by dp. So this is going to be 1 over 5, and we end up with this expression. So let's just go ahead and simplify it first. 124 divided by 5, we get 5 from 80 minus 75, and we factor out the 124, just so we have one less number to deal with. And so we end up with p divided by 10 plus p and 100 minus p dp. So we're going to use partial fractions to evaluate this integral. And it's a definite integral in this case. It's not a indefinite integral, but we're going to do the whole partial fractions thing by itself. And then we will plug that in once we get the answer. So we had 2 distinct linear factors, and these are it. So because they're distinct linear factors, we're going to have a times the first term plus b times the second term, which reminds me, if you go back to the logistic growth function, you can see how we used the method of partial fractions to be able to solve that equation. Okay, so what do we do now? Well, we find a common denominator, and so we're going to multiply this fraction by this in both the numerator and the denominator. We're going to multiply this fraction by this in the numerator and the denominator, but we can just do a cross product when we have 2 terms. So we have p on the left-hand side. On the right-hand side, we have a times 100 minus p, and then we have b times 100 plus, or 10 plus p. And because they're distinct linear factors, the easiest way is to let p equal either 100, which will make that term go to 0, or we let p equals negative 10. Now you say, well, can you really have a p of negative 10? Well, mathematically you can. So we can do it mathematically to find the constants. So we're going to let p equals negative 10 over here. So we'll do these separately. So we have p is 100. We have a times 100 minus 100. So that goes to 0. Plus we have b times 10 plus 100. So b, since this goes to 0, you just have 100 divided by 110, so we get 100 divided by 110, but we can factor out of 10, so we get 10 11ths. And then over here we do the same thing. We have 100. Actually, we don't have 100. We have a negative 10. So p is negative 10, and we have a times 100 minus p, which is a minus 10. And then the second term is going to be 10 plus negative 10, which is 0. So I'm just going to say that's 0. So we'll end up with 100 plus 10, which would be 110. So we get minus 10 divided by 110. And therefore A is equal to negative 1/10. So those are A and B. So now we can plug those into our expression here and get the integral. So we started out with, what was it, 124 over 5. And the integral we have the integral from 75 to 80 of 2 terms. We have A, which is negative 1/10, so we get negative 1 over 10 times this denominator, which is 10 plus p. And then the second term is b, which is 10 11ths, so we get plus 10 divided by 11 times 100 minus p. And everything here is going to be multiplied by dp. So this is multiplied by dp. So if we go back, we had this integral right here, actually this integral right here. By using partial fractions, we can break it up to two terms. Okay, now what happens? Well, if we do each one of these separately again, you're going to get a negative 1/10 that we can factor out. And then the integral of dp over 10 plus p is just going to be equal to the natural log of the absolute value of 10 plus p. So that's the first one. The second one is also negative because we have a negative p here. So when you take the derivative of that, you get negative dp, which means you got to multiply and divide by negative 1. So we'll have 10 elevenths times the natural log of the absolute value of 100 minus p. And we evaluate that between 75 and 80. Okay, let's simplify this a little bit. And I just realized I made a mistake. This should be 11, not, so it's 1/11. Let's figure that, fix that. So this would be 1/11 as well. And this is 1/11. I knew that because these should have the same denominator. So you can factor out a negative sign. So you'll have a negative 124 over 5. And then we can also factor out 11. And so what does that leave us? That leaves us a natural log of 10 plus p plus the natural log of, actually, we've got to put that 10 in there. So we have 10 times the natural log of the absolute value of 100 minus p. And you could kind of combine these together, and don't see why not. It just seems we're going to have 100 minus p to the 10th power, which bugs me a little bit. So before we go any further, let me just cheat a little bit before I plug that in and get all confused. So this is problem number 59. And well, looks like it's right. So they don't actually combine these two. They just leave them as they are and then plug in the numbers. So let's just do that. So now we can evaluate this at the upper and lower limit. So we have negative 124 over 5 times 11 is 55. So what we're going to have is we're going to have the natural log of 10 plus the upper limit, which is 85, plus 10 times the natural log of 100 minus 80. Well, actually, it should be 80, not 85. So that becomes 80. This becomes 80. And then we subtract it off at the lower limit, which is the natural log of the absolute value of 10 plus 75 plus 10 times the natural log of 100 minus 75. Let's make sure we did that right. That's correct. 80, 100 minus 80. Subtract the lower limit, natural log of 10 plus 75 plus 10 times the natural log of 100 minus 75. So let's plug those in our calculator. So I'm just going to do the internal part first here. So we got the natural log of 90 plus 10 times the natural log of 100 minus 80, which is 20, minus the natural log of 85. Minus 10 times the natural log of 25. And for all that, I get negative 2.0 717. So I get negative 124 over 55 times negative 2.174. So we multiply that by negative 124, divide by 55, and I get 4.90. And if I check the answer, so that's 4.90, and the problem statement was in hundreds of thousands of dollars. So the actual answer, the actual average value for C, so C average, is $490,000, which is the answer that's given in the book. So we must have done that correctly. So let's kind of review what we did. We said this was the cost as a function of the percent chemical removed. And if you look at the data, you can see it gets more expensive as you take more out. We went between 0 and 100%. So that was our domain. The average is 1 over B minus A, which are the limits that we're talking about. We wanted to go from 75 to 80%. 1 over B minus A times the integral from B to A, from A to B, of the function. We factored out 124, and we divided by 5. We use partial fraction decomposition to make this fraction here into these two separate fractions. We had to find constants A and B, so we multiplied A times this denominator plus B times that denominator because they're just two independent linear factors, two distinct linear factors. And then we let P go 100, so this would go to 0. We could solve for B. B was 10/11ths. We let P go to negative 10. Even though that's outside the domain, we can still do that in terms of the math part. When we actually apply it for the answer, it has to be between 0 and 100. So that'll allow that to go to 0, and we can solve for A, and we get negative 1/11th. So our original integral here, which was something we didn't know how to integrate, became this, which we do know how to integrate because we just have dP over a term that we can set equal to u and take the integral and get the natural log of the argument. And then what I did is, so we had negative 1/11th, which we factored out here, and the integral of dP over 10 plus p is the natural log of 10 plus p, and the integral of dP over 100 minus p is negative the natural log of 100 minus p. And then we evaluated it at the upper and lower limits. We also factored out a negative 11th, so that became 1, and this became positive 10. And then when you evaluated at the upper and lower limits, you get 4.9 as the answer, which, because the formula was given, so the results were in hundreds of thousands of dollars. Instead of 4.9, we have $4.9 which is $490,000. So that's the problem. Hopefully that made sense.